So the concept of a random vector is a fairly straightforward one. The idea is just that if I have n random variables, I collect them into a n by 1 vector like this, and this will give me an n by 1 random vector. Based on this, it seems rather natural to define the expected value of a random vector as an n by 1 vector where each element is the individual expected values. In row 1, we have the expected value of x1 and so on to row n, where we have the expected value of xn. Since we typically denote the expected value of xi by mu I, we can also write this as the vector mu1 to mu n, noting that this is a simple n by 1 vector of constants. So in vector notation, it's common to write this just as a mu, which in print is then typically boldface. So the expected value of an n by 1 random vector is an n by 1 vector of constants. So we need to figure out not just the expected value of the random vector, but quite often we need to know the expected value of a function of this random vector. And the result is fairly straightforward. So if x is my n by 1 random vector and it has a joint PDF, which is f of x, this is now a function of n variables. If I then have a function g from Rn to R, such that g of x is a random variable, then the expected value of this random variable, g of x, can be calculated as the integral over all of Rn, all possible values for all of the variables. We do g of x. G is a function of the n variables x1 through xn, and it returns a number. So g of x is a number multiplied by f of x, the joint PDF. This is also a function of the n variables x1 through xn, and it returns a number, dx, where dx is just shorthand notation for dx1, dx2 through dxn. If g is a function from Rn to Rm instead, then g of x will become a random vector. It will become an m by 1 random vector. Since we can write g of x in vector form as g1 of x through to gm of x, a vector valued function, that is a function that returns a vector in Rm, can always be written in this form. That is, I can always break this into m functions, where each of these functions, gj, is a function from Rn to just R. In this case, the expected value of g of x will become equal to expected value of g1 of x down to expected value of gm of x, where each of the elements in this vector is calculated using the previous formula. So the expected value of gj of x, where j is any number between 1 and m, is simply the integral over Rn gj of x f of x dx. And we have to calculate this integral m times to get the expected value of g of x. So a very important case, as always, is the case when g is linear. Let's begin with the simpler case where g is a linear function from Rn to R. Then we know that we can write g of x as c prime x, where c is just this vector c1 through cn of constants. In this case, the expected value of g of x should be the expected value of c prime x will be equal to, we can just take this constant outside, c prime expected value of x, or if you like c prime mu, where mu is the expected value of x, an n by 1 vector of constants. Note that this thing here will come out to be a scalar 1 by 1, which it should be because this is a simple random variable now, not a random vector. It's not hard to see exactly why we can move this c outside the expectation. The expected value of c prime x is the expected value c1 x1 plus cn xn. Since this is a linear function of n random variables, I know that this is equal to c1 expected value of x1, cn expected value of xn, which in vector notation is precisely c prime e of x. Finally, let's look at the case when g is vector valued, so it's from Rn to Rm. Then, if g is linear, we can always write it as a matrix times x, where A is an m by n matrix, such that Ax is m by 1. In this case, the expected value of g of x, keep in mind this is now a random vector, that is the expected value of A times x. We can still take the entire matrix A outside, is A times E of x, which is A times mu. Again, it's not hard to see exactly why we can take the matrix outside. If A is this matrix, A11 to A1n, all the way to AM1, AMN, then AX is just this vector, A11, x1 plus A1n, xn, down to AM1, x1 plus AMN, xn. The expected value of AX, well, that's the same m by 1 vector, and we take the expected value of each row. The expected value of the first row will come out to be A11 expected value of x1 plus A1n expected value of xn, and the last row AM1 expected value of x1 plus AMN expected value of xn. And you can easily convince yourself that this is precisely the A matrix times the expected value of x vector, which we can write as A times mu.